Hi, so this is just a short video, or hopefully a short video, to describe where the formulas for compound interest come from a calculus perspective. All right, so let's just start off. So the first kind of interest you've learned about, and I won't spend a whole lot of time with this, is simple interest. And simple interest is if you want to know how much interest you accrue in a savings account after a certain time period, that total interest measured in dollars would just be the principal times the rate times the time, where the interest rate is measured in as a decimal point per year. So instead of a percent per year, as you usually express it, you convert that percent to a decimal, and then it's the interest accrued per year. And then the time would usually be measured in years. And then the accumulated value after so many years would be the original principal plus the interest. Let me write it like that. Which again is the same thing as just saying P plus PRT, because that's what their interest is. It's principal times rate times time. For simple interest, you could factor out a P, and you can write this as P times 1 plus RT. Okay, so I hope that's okay. And the idea of simple interest is that your interest doesn't earn any interest. So if you were, if your savings account was making 6% a year, and you've left the money in for 3 years, you would just be getting 6% a year. So 6% plus 6% plus 6%, because there's 3 years, you'd be making 18% on that money. So it would just be 18% times the original amount plus the original amount again, which is the same thing as doing 1 plus that 18%. All right, so that's the idea of simple interest. Compound interest is the way most things tend to work. Interest can be compounded daily or monthly or semi-annually, and there's a lot of different options. Monthly is pretty common, so I'll just use that as a simple example. So for example, if we were doing, if we had a savings account that was paying 6% interest per year, compounded monthly, for let's say 2 years. We do have a formula for this, but let's say we didn't know the formula. So what would be going on here is that the idea behind compound interest is that if it's compounded monthly, you're going to be earning 6% interest over the year, and that's equivalent to 6% divided by 12, so 0.5% per month. So instead of 12%, so instead of 6% a year, it's 0.5% a month. And while that sounds like it's the same thing, it really isn't, because that 0.5% a month is then going to be put back into your account. And if you don't touch it, it's going to start earning interest as well. So that's where this whole compounding comes from. So really 6% a year compounded monthly will work out to be really more than 6% if we were trying to accomplish the same thing with simple interest. So the idea is that at the beginning, the total amount that you would have in your account, which I'll just call A, is just going to be the original principal, your original starting amount. But after the first period, so at the end of the first month, beginning of the second month, however you want to look at it, we'll say at the end of the first month, you're going to have your initial amount times, well, we would normally do 1 plus RT, but let's think about this for a second. So what this is really going to be doing is you're not earning 6% on this. It's 6% over a whole year, but we're only looking at 1/12 of a year. So really, you're just getting 0.5%, which is 0.005 for that period of time. But keep in mind, this really is essentially R times T that we're talking about here. Our interest rate was 6%, which is 0.06, and our time period is really 1/12 of a year that passed. And if you do R times T, you would get 0.06 divided by 12, or 0.06 times 1/12, which is the same thing as saying 0.005. So earning 0.5% over the course of a month is the same thing as earning 6% over a year when you're compounding monthly. All right, so I hope that makes sense. So really what's going on here is that after at the end of the first month, you would take the initial amount that you put into your account, $100, $1,000, whatever it is, and multiply it by 1.005. Okay, at the end of the second month, you're going to have what you had from the previous month, which was that 1 plus 0.0005, but you're also going to earn interest on that. So you're going to have another 0.5% interest on that at the end of the month. At the end of the third month, it would be the same thing. You're going to have what you had at the end of the second month. So the principal times 1.005 times 1.005. And then again, you're going to have to multiply that by the interest you earned that month. Okay. And this trend is going to continue. So we're compounding monthly for 2 years. So how many compounding periods will there be? Well, if we stopped at 1 year, we would stop at 12 here. That would be the end number. But we're going for 2 years, so it's going to be 2 times 12, because there's 12 compounding periods a year. Basically, compounding monthly means that there's 12 periods a year, and n is how many times it's compounded a year. So n is 12. And it's going on for 2 years. So it would just be 12 times 2, which is 24. And continuing along this trend, it would just be p times 1 plus 0.005, which is the same thing as doing 1.005. And you're going to keep multiplying this a whole bunch of times. Let's see if we can see a trend. So at the end of the first period, there was one of these things being multiplied. At the end of the second period, there were 2. At the end of the third period, there were 3. So at the end of 24 months, there should be a total of 24 of these things, which is the same thing as doing p times 1 plus 0.005 to the 24, because there's 24 times this is happening. So if we want to figure out how much interest we're going to earn, it's going to be the original amount you start with times 1.005 to the 24th power. And that's it. All right, let's try to put this a little bit more generically. So in other words, I'm not going to mention what n is this time, and I'm not going to mention what t is. We'll just call n, and we'll just call t, and read you the same kind of a calculation. Let me actually do this on the same screen. So here's the idea. This final number we knew was 24, but how did we get 24? We got 24 by taking the number of compounding periods and multiplying it by the time, the number of years that passed. So this number is just going to be n times t. Okay, p is obviously still going to just stay p because I didn't give you a starting amount in our account. And then again, we have this 24, which we figured out was n times t. Right, so this is n times t. This 0.005, how did we get that? Well, we got that by taking our interest rate and essentially dividing it by how many compounding periods there are in a year. So our interest rate was 6%, and we divided it by 12 because 6% over an entire year is the same as 0.5% a month. And we figured that, and we got that by basically just taking the 6% and dividing it by 12. So the interest rate divided by the number of times it's compounded per year is going to give you the basically that interest rate per period. All right, let's put all this together and we get our compound interest formula. So our formula for compound interest is going to be our accumulated value after so many years, after 2 years, is going to be your principal times 1 plus the interest rate divided by the number of times it's compounded per year, raised to the n times t power, which is the total number of compounding periods, period. All right, so this is compound interest when you're dealing with interest that compounds n times a year. But we could also approach this in a calculus type sense, where what happens if instead of compounding n times a year, where each of the times your interest is compounded, it's not the 6% that you're looking at that's compounded, it's 6% divided by however many compounding periods there are in the year. So what if we basically said, okay, there's going to be 1,000 compounding periods in a year, and each time it's compounded, it's your interest rate divided by 1,000. Let's take it to extreme. Instead of saying 1,000, let's say infinite. So there's an infinite number of times your interest is compounded per year, but each of those times the interest is compounded, it's basically your interest rate divided by infinity. I know that sounds a little weird, but you're getting a very, very, very small amount of interest every moment, and then there's an infinite number of moments throughout the year. So putting this a little bit more formally, what we're talking about is we're saying there's like basically what's going to happen to A as n approaches infinity, when there's an infinite number of compounding periods per year. And again, this is called continuous compounding or continuously compounded interest. Okay. Sorry for this slightly messy handwriting. All right, so let's use limits. So we're saying what's the limit as n approaches infinity of A? And remember, A is defined as P times 1 plus R over N to the NT. All right, to approach this, we're going to need to know a lot of different limit rules. Maybe we should even start this on a separate page. So we want to find the limit as n approaches infinity of P times 1 plus R over N raised to the NT. Some of the rules we're going to need to know, just because I've done this before and I'm familiar with what we're going to wind up, where we'll wind up going, is we do have a definition. We have the definition of this natural number E. And E is defined as the limit, and you can use any letter you want. We can call it M, we can call it X, we can call it H, it doesn't matter. I'll just call it X. So it's the limit as X approaches infinity of 1 plus 1 over X raised to the X. And if you take out a calculator and you try to plug in, let's say, X equals 1,000,000, X equals 1,000,000,000, X equals 1,000,000,000,000, you'll see this 1 plus 1 over X raised to the X power is going to approach this number 2.71828. And this number does keep going on forever. It's kind of like pi, where it just never ends. But we can use it in a calculator, in a computer. So if we, at any point in time in our calculation, see something that looks like this, we could just replace it with E. Other little facts we need to know is that if we have a number, we can call it maybe A raised to some power, let's call it the BC power. That's the same thing as saying A to the B power, all that raised to the C power. Often you see this rule going this way, where if you have something raised to a power, raised to another power, you can multiply the powers, but it does go both ways, where we could separate things out. Another rule is one of our limit rules. And one of our limit rules is that if you want to find the limit, actually there's two limit rules I want to show you. Let's say, just for an example, we say the limit as X approaches some number A of f of X is equal to some limit, we'll call it L, then the following facts are true. So there is a limit defined, and A could be a number or A could be infinity, it doesn't really matter. So if we have the limit as X approaches A of some constant, we can call that constant maybe C times our function, then this is just going to be C times the original limit. In other words, if you have a constant multiplied by a function, you can move that constant out. You don't have to take the limit of the constant. Another rule is that if you want to find the limit as x approaches a of that function, which we know has a limit, but it's not just of the function, it's maybe the square root of the function, or maybe that function to the 8th power. Basically, if this function is being raised to any power, I'll call this power p for power. This is going to be the same thing as basically just taking the limit of the function, which we said was L, and raising that to the power. All right, so we're going to need all 4 of these rules in order to tackle this question. So let's keep those in mind. We've learned about all these rules before, so let's move on. All right, so the first step, and again, this is not obvious that this would be your first step. It's just because I've done this before that I know that this is the first step. I'm going to create a new variable. Let's call it m, because why not? And I'm going to say m is equal to n divided by r. And what this is going to mean, because, well, in a practical sense, wherever we see n over r in the original thing that we're trying to evaluate the limit for, remember we're trying to figure out what this limit is, wherever we see n over r, we can replace it with m. But at no point do we see n over r, so that's not totally helpful. But we could solve this for n, because we do see n in several places. There's 3 n's in this thing. And wherever we see n, we can replace it with m times r. All I did was multiply both sides by r. So I took this, this variable I created, m over n. I'm sorry, this variable I created m, which equals n over r. Sorry for misspeaking. And just multiplied both sides by r to solve for n. All right, long story short, sort of. Wherever I see n in my original limit, I could replace it with m times r. One other thing to note is that if n approaches infinity, right, because we know that n is going to approach infinity, that was our original thing. I'll use another color, I'll use yellow. Originally n approaches infinity. Well, that means that m times r must approach infinity. But another thing to keep in mind here that r is a constant. So if n approaches infinity and m times r approaches infinity, m by itself must also be approaching infinity because r is a constant. It's not approaching anything. R is just a number. So, well, I mean, it's approaching the number. It is the number. So if m times r is approaching infinity, then m must be approaching infinity as well. All right, so let's rewrite this. And every time we see n, we're going to replace it with m times r. So this is going to be the limit as, I want to write m times r approaches infinity, but that's a little bit weird. But remember, if m times r approaches infinity, that's the same thing as m approaching infinity. So I can do that pretty safely. And this is going to be p times 1 plus r over n. But remember, wherever we see n, we want to replace it with m times r. And it's times nt, but wherever we see n, we replace it with m times r. So it'd be m times r times t. All right, it may not be obvious, but we are making some progress here. These r's are going to cancel. And so this is the same thing as saying the limit as m approaches infinity of p times 1 plus 1 over m raised to the m r t. All right, we really are getting very close now. Using the limit property that we can pull constants out, this property here, we could pull out the p, because the p is the principal, the starting amount. It's just a constant. It's something we determine before we start making these calculations. So I'll pull out the p, and I want to find the limit as m approaches infinity of 1 plus 1 over m raised to the mrt. Wait, we also have that other rule with exponents, where if we have something, right? If we have something raised to a power, we could just break it apart. And so instead of a to the BC power, we could say a to the B power, and then raise that whole thing to the C power. So using that rule, we could rewrite this a little bit more. And this would be the limit as m approaches infinity of 1 plus 1 over m to the m power, and all of that being raised to the RT power. So I just split apart that power. All right, one last thing is we have this final rule, that if we know the limit of something, like if the limit of something is L, then if we take that same something and raise it to a power, the limit would be L to the P. So in other words, I could rewrite this even further and say this is P times the limit as m approaches infinity of 1 plus 1 over m raised to the m, and whatever that limit is, raise that to the RT. Okay, last step. This, hopefully you recognize. The limit as m approaches infinity of 1 plus 1 over m raised to the m. I'm using m instead of x, but that is exactly our definition of E. It's the limit as x approaches infinity of 1 plus 1 over x to the x. Same thing. So we can rewrite this as P times, again, all of this is really just E, and that E is being raised to the RT. Whew. Okay, so that's our conclusion. Long story short, if we have interest that's continuously compounded, meaning every moment you're going to be earning interest, but the interest you're earning is very, very tiny, infinitesimally small. So if you have continuously compounded interest, the final amount that you're going to have, the accumulated value after so many years, is going to be P times E to the RT. And it's derived entirely from the compound interest formula, which is derived from the simple interest formula, where you're literally just compounding every month or every moment or every period that you're talking about. And that concludes this video.